continue our section 1.3, evaluating limits analytically. So we have in section 3.1.3 we have theorem 1.1 to 1.9. Instead of write out the theorem, I'm just gonna explain to you which theorem mean which. The first one, theorem 1.1, is said that if you have a limit of a constant, so limit of 3 as x approaching 2, you're going to get constant, which is 3. So the limit of a constant is the constant. The second example, also from theorem 1.1, you have a variable, and if you have limit as x approaching -4 of some variable, you can do direct substitution. In this case, it's going to be -4. The third one is still in theorem 1.1. I have a function x squared. Again, I can do direct substitution. I'm going to substitute 2 for x, so I'm going to have 2 squared, which is 4. So that is theorem 1.1. Now theorem 1.2 states that if you have 2 or 3 functions, add to each other, multiply each other, or divide each other, if you can do direct substitution, just do direct substitution. In this case, as x approaching 1, so I'm gonna replace all the x with 1. So I would have 3, 1 to the cube, minus 2, 1 square, plus 4. Alright, direct substitution. So I would have 3 minus 2 plus 4, which is 5. So that's theorem 1.2. Theorem 1.3 states that if you have a rational function which look like fraction, but it's called rational function, and if you can do direct substitution, you will do that. Now if I substitute -3 in here, I don't get 0, so I can do direct substitution. So I would have 2 -3 plus 2, which is 2 over -1, which is -2. However, if you do direct substitution and you get undefined, you have to use other method. Now, theorem 1.4 states that if you have a radical and if you put as x approaching some number here and you can do direct substitution, you can do so. So we're going to have cube root of 4 plus 4, which is cube root of 8. Cube root of 8 is 2. Theorem 1.5, if you have 2 functions and you want to do composition, again, you're allowed to do direct substitution. I have f of g of x. So the inside function is the f of x. So if I'm going to do direct substitution, I'm going to have limit as x approaching -3. Instead of f of x, I'm going to do x plus 7. Now my x, I'm going to replace it by -3. Then I will have g of -3 plus 7, which is g of 4. Now you go back, g of 4 is x squared. So I would have 4 squared, which is 16. Right? The next one, theorem 1.6, talk about trig function. So again, I will do direct substitution here. So I will have tangent of pi, because x approaching pi. Tangent of pi is sine of pi over cosine of pi. Sine of pi is 0. Cosine of pi is -1, so it's equal to 0. Alright, let's look at more theorem here. Let's look at our next theorem, theorem 1.7 to theorem 1.9. Again, I would like you to read that from the book. Theorem 1.7, let's look at the first example here. The first example, I have a limit of this function. Let's say if I try to do direct substitution, when x equal to 0, I will have 0 plus 0, which is 0, then it would be undefined. So the direct substitution doesn't work. So I'm going to use dividing out technique. So theorem 1.7 allow me to do that. So I'm going to rewrite this as limit as x approaching 0, 3x. I'm going to factor out the x here. So I'm going to have x plus 2. After that, I'm going to reduce the x here. So I would have limit as x approaching 0, 3 over x plus 2. So basically the theorem said if you do direct substitution and it's failed, you're allowed to simplify it. So you simplify this to the point that you can do direct substitution. Now if I substitute 0 for x here, it's okay. It doesn't make it undefined. So I'm going to have 3 over 2. So the answer is 3 over 2. Alright. Let's look at the next example. If I'm going to do direct substitution, again I have 0 on the denominator. The expression is undefined. I can simplify this, so I cannot apply the dividing out technique. So I'm going to use rationalized techniques. So I'm going to multiply by its conjugate. So I'm going to write as limit x approaching 0, square root of x plus 1 minus 1 over x. That's the equation. Now I'm going to multiply by its conjugate, which is x plus 1 plus 1. Alright, so the denominator will be square root of x plus 1 plus 1. So this whole term basically is equal to 1, so it doesn't change the value of this. So if you remember the difference of square, think of a minus b times a plus b. Alright, so I'm going to use the difference of square here. So the numerator, I'm going to have the first term square, which is x plus 1. If you square this, you just have x plus 1, minus the second term square, which is 1. I'm using the formula a minus b times a plus b equal a square minus b square. That's called difference of square, right? So that's what I'm going to get in the numerator. Now the denominator, I'm going to have x times this square root of x plus 1 plus 1. Alright, now I'm going to simplify this a little bit. So limit as x approaching 0, plus 1 minus 1 cancel out. So I left with x square root of x plus 1 plus 1. Again, x approaching 0 but not equal to 0. Alright, it's just approaching 0. So I'm going to reduce this. So I have limit as x approaching 0, 1 over square root of x plus 1 plus 1. Now I can do direct substitution. If I substitute 0 in here, I get 1. Square root of 1 is just 1, so I have 1 over 2. Alright. Now the next theorem is called the Squid theorem. So let's look at the example here. I have a limit of this function as x approaching 0. I have a limit of x approaching 0 of f of x, and also another limit of another function. And they want you to find the middle one here. Alright, so the first one here, you can use direct substitution. If x equal to 0, limit of this whole thing would be 4. So I would have 4 less than or equal to limit as x approaching 0 of f of x less than or equal to. Again, from this one, I can do direct substitution as well. If I substitute 0 in here, then I get 4. So this limit as x approaching 0 of f of x is between 4 and 4, so it has to equal to 4. So limit, actually it should be phi limit, yeah, as x approaching 0 of f of x. So limit as x approaching 0, f of x is equal to 4. Because it's greater than or equal to 4, less than or equal to 4. It has to be 4. Alright? So that's theorem 1.8. The last theorem of this section is theorem 1.9. Is two special trigonometry function. So just memorize this. We'll probably do the proof in the Zoom or some other time. So limit as x approaching 0, sine of x over x always equal to 1. Limit as x approaching 0, 1 minus cosine of x over x is going to equal to 0. Alright, we finished 1.3.